Yes, Shubham Jane, very good morning. Previous class discussed all that concepts regarding work, conservative force, non-conservative force, and the concept of potential energy. Friends, I would like to add one or two more points for our discussion. It happened last session that you remember we have given that expression, the relation between the conservative force and the potential energy as F equal to negative of course du by dx, dr or whatever we have said. This expression, one important point I would like to make. If this refers to the displacement term and this refers to the conservative force, then look at this term du. So what does it mean here? That is, this du refers to the change in potential energy. This du is a change of potential energy such that now a very bold statement is that for any given system, if it has potential energy, the absolute potential energy we can never determine. Remember, statement is, whenever we say potential energy of a particle, potential energy of a body has no meaning at all. We should never use that usage. Potential energy of a particle, no. Potential energy always refers to that of a system. Supposing even when you said that, potential energy of a body, mgh you said. You may now give a kind of argument with your teacher. Sir, last year we have calculated that potential energy equal mgh for a body. It was a very loose statement if it is said like that. It is what is the potential energy of that body and earth system. mgh, potential energy of the body is a very loose statement. Potential energy of that body and as well as earth system. And one more time, that mgh is not the potential energy. Rather, in fact, it is what is the change in potential energy. Change in potential energy. Whether potential energy has increased by this amount mgh or decreased by that amount mgh. So our statement is potential energy is always refers for a system. And the second point is that there is no absolute potential energy that we will calculate ever. It is always the change in potential energy that we evaluate. That change can be either positive or negative. That is, it is either increase in potential energy or decrease in potential energy that we actually evaluate or we calculate. Because potential energy is a kind of inherent energy of a system. It is inherent due to its state, the state of the system, or you can say the configuration of the system. Configuration means the arrangement of the constituents of the system. Because of all this, the system has a naturally acquired energy which we call inherent energy. So potential energy is a kind of inherent energy. No absolute potential energy we can ever evaluate. Even today whatever the topics that we follow, it's all referring to change in potential energy, right? So these are two more important points I wanted to tell you. Now let us get into our second unit according to NCERT's book. Now, the naming of the unit and further. Let us continue. Yeah. Now you can look at the title. Our title is Electric Potential. Right. Now, since Coulombic force is a conservative force, electric field is a conservative field. So the concept of conservative field and displacement, whenever it arises, there comes the question of potential energy. And that is why we had made all that detailed discussion about the work and potential energies. Now, let me consider an arbitrary electric field. What is meant by arbitrary? Some electric field whose origin is not important for us. The field due to a configuration of charges, maybe a single charge or multiple charges whatsoever. Supposing now here I show an electric field represented by these electric field lines. Okay. And in this electric field, I choose 2 points. Now I am choosing 2 points. Those 2 points, this point, I will call this point P, and another point somewhere over here. Okay, this point is Q. So P and Q are referring to 2 points inside the electric field. Now, let me now assume a test charge. You remember what we have said about the test charge? Why test charge is taken to define any other parameter in electrostatics already you did. And test charge is always positive. Now here I consider a test charge. I will hope you can see it. Now assume a test charge. I am writing it as plus Q0. Green color. Can you watch it please? Yes. A test charge now assumed at P, and let us imagine that this test charge is displaced from P to Q, and this displacement, 2 aspects. Number 1, displacement without any acceleration. Displacement without any acceleration means displacement with uniform velocity. Second point, of course, when we are displacing this test charge from P to Q, the path is immaterial for us because yesterday's statement was work done. In the case of conservative force is always independent of path. For now, a test charge moved from P to Q with a uniform velocity. What is meant by this uniform velocity? Uniform velocity means acceleration 0, net force equal to 0. Net force equal to 0 means, yes, the applied force is equal to, applied force on this Q0 is equal to force acting on this Q0. The forces are equivalent, opposite, net force is 0. Now remember here, the charge that we have taken is a positive charge, and we are displacing this charge against the field. Because whenever the case of potential energy arises, I have told you, we will take the case of against the field, against the force. Now here also, P to Q, it is displaced. And for this displacement, of course, it is against the Coulombic force. Because when we are tending to displace this Q0 from P to Q against the force, that is, the Coulombic force is there, and the overcome Coulombic force, now we have to do work to displace this charge from P to Q. Now I'll make a mention of our discussion in 2 statements, right? Let a test charge, let a test charge be displaced from point P to Q, from point P to Q with uniform velocity. This is mentioned, of course, because when there is uniform velocity, now the work we are referring to, whatever work is done, that work will be only causing the change in potential energy, but no change in kinetic energy. So our final expression we will take it as work done equal to change in potential energy. So with uniform velocity against, now the most important point is this against the Coulombic force. Against Coulombic force. One more important thing, that when we have set uniform velocity, net force equal to 0, for net force equal to 0, what does it mean? The applied force, the external force applied on the test charge is equal to Coulombic force acting on the test charge. Therefore, here whenever we say force and force, external force, but we will equate it with the Coulombic force for this reason of uniform velocity. And of course, as you know, our yesterday's discussion, W is integral. Why we are taking this integral force? Because you know here that P to Q, when you are moving, the force is not a constant force, right? Therefore, it's a variable force, and that is why we are now writing W is equal to integral F dot some ds F dot ds bar. And this work done, yes, this work done equal to change in potential energy. Now I can make this statement very open and bold because of 1 hour discussion almost we did for understanding that. This work done, W, is now equal to du, the change. Now, let me now write specifically as W from P to Q. The work done in moving from P to Q equal to, yes, UQ minus UP. Look here, this is a very important statement for us. When we do with numericals and all, this is an important statement. W, P to Q. Here, the order is important, right? The work done in moving the test charge from P to Q is equal. This is initial position and this is final position. Now look at the RHS. As usual, the change is always final minus initial. So UQ minus UP. And one more time, this left hand side does not depend upon the path. Does not depend upon the path. Depends only on the initial position and the final position, right? Now, when we look at this W, W is equal to integral F times ds bar. Remember, now we are saying this W equal to integral. What is that F? You remember our definition, E times Q naught times ds bar, right? Because this was our definition. F is equal to EQ, E equal to F by Q, all that now it is made use. Remember, in physics it is a ever continuity. Chapter 1 is over, chapter 2 is something different. No, day 1 to day last. Day 1 to day last, it will be continuity every class. Not like, unlike other subjects, you do your approach, chapter 1 is over, chapter 3, independent, you will never get. Ever continuity, you please follow. This is E times Q naught times ds bar. So now here, whatever you find that this W which we are referring to, or the potential energy that we are referring to, the point is, depends on two aspects. In the field, at each and every point, look at this UQ minus UP. What does it answer? In a given electric field, at each and every point, there is potential energy such that that potential energy we are talking about of the system, of course, it depends upon the charge that we have considered, this Q naught. Right? Now, we want a parameter which is purely a characteristic of electric field, not depending on any other aspects. This E refers to the character of the electric field, right? Therefore, now we want a term which is independent of we are referring to energy character of a field, and that should be independent of the charge under consideration. Therefore, to do that, what we do here is now that this potential energy or this work, both are equal, right? Upon charge we take, this is what is Q naught. If you take this term, then that will be independent of the charge, and that is what is our electric potential. So potential is nothing but a term referring to potential energy, but with a specific condition. That condition now we will mention. And one more important point, please do remember that earlier we have considered both these points P and Q, both are well inside the electric field. Now, as I have told you, absolute potential energy we can never measure, we can only calculate or evaluate the difference. No absolute potential energy. Therefore, now with that convenience, now we have a choice. We have a choice of giving some reference. That is, whenever we say zero potential, what is that reference? Here, any point outside the electric field, we take it as an infinite point at infinity. At that point of infinity, the potential energy is taken to be zero, assumed to be zero. Therefore, this is what is a reference that we are now evaluating. What is that reference now means? Therefore, now look at this statement. This is what is the work done in moving from P to Q, final minus initial. Supposing if P is at infinity such that UP is equal to 0. Now the question comes, sir, is it always 0? Can we take any? You can take any quantity, because as I have told you, no absolute potential energy. But why I am taking 0 here? Supposing morning I had some zero amount with me, and by evening, supposing due to some interaction, I had some 200 rupees. Now what is the money with me is 200. The gain is also 200. Is it not? And that is why for that advantage or for that convenience I am taking that initially for the point P at infinity, UP is equal to 0. In such case, what happens? Work done from P to Q, yes, work done from P to Q is simply equal to, yes, the energy at Q. So that is how the change in potential, though it is, now it refers to energy at that point. Energy at that point by the convenience of some taking a convention. What is that convention? At infinity, the potential energy is 0. Therefore, now we see that potential energy of a system at infinity is 0 due to the system of charges. And second important point is that potential energy that we have referred to depends not only on the characteristic of the field but also on the charge. Therefore, now we want to make that charge independent, and there comes our concept of electric potential. Let us see the definition. Now, this is all our introduction. Now, I will define potential and I will do some small work based on our NCERT syllabus. Let us see that. So, this is how we define potential at a point. See, the work done in displacing a test charge. In fact, one more word is required. With uniform velocity is there. If you write it, yes, it speaks about your method. The work done in displacing a test charge from infinity to a point in an electric field is called potential at that point. Remember, when we have defined intensity, intensity is always defined at a point. Now, when it comes to potential, we can have two ways. Potential at a point. Second one is potential difference between 2 points. Now let me show both the cases. First, I have defined potential at a point, right? So the potential at a point V at a point P is the work done in moving a test charge with uniform velocity from infinity to P upon this Q naught. This Q naught, right? So this is what we have defined, potential at a point. Potential at a point. Supposing if both P and Q are inside the electric field. In this case we have taken initial point P outside the field, which we call infinity. And infinity always refers to, remember, it is a relative sense. Where there is no effect of field, that point refers to infinity. It does not mean literally infinite means too long distance. No. It is a distance at which the effect of field is not present. Now supposing if I am writing it as V VPQ. VPQ. What is VPQ? Remember, VPQ refers to the potential difference. Now I am writing VPQ refers to VQ minus VP. Look at this order. Here VPQ. It conveys a meaning that the charged particle is now displaced from P to Q. In such case, this is what is VQ, the final point minus initial point, the potential difference, right? VQ minus VP equal to the work done in moving the charge from P to Q by Q naught. This is potential at a point, or this is potential difference between 2 points. Now, let us see the case of writing the units, the dimension formulas and all. Now, you can see that known to unknown. I need not tell the unit here. Already we know the unit for work, the joule per coulomb, right? So the SI unit for electric potential or the potential difference that we are referring to, SI unit is, yes, joule per coulomb. Joule per coulomb, and it is completely converted into pure electrostatic units, and this joule per coulomb is what is called as volt. When you are writing the full form, look here, this is a small v, and of course the symbol is capital V, refers to volts. And since this is a work analog or energy analog, this is a scalar quantity. So electric potential is a scalar quantity, right? So potential, whenever I mean potential, please make it sure it is electric potential. So potential is a scalar. Potential is a scalar. This is again dimension formula. When it comes to dimension formula, you know that joule is mL square T minus 2. Coulomb means IT. Therefore, now I am here writing the dimension formula is, yes, mL square T minus 2, and in the denominator you have IT, so it is mL square T minus 3 I minus 1. Whenever this kind of dimension formula comes, please do remember it is not a memory. If you make a memory, it's a complete mess up and stress. At the correct, at the essential right time of your challenges, it makes a big difference. So just from known to unknown, you make your journey. This is mH square T minus 3 I minus 1 is what is electric dimension formula. Now, let us do some simple cases of finding the electric potential. The same we did earlier, you remember? When we defined electric field, we did the cases of intensity due to point charge, intensity due to dipole, blah blah blah. The same way here also, now we do a very important concept of potential due to point charge. Let us see that. Yeah, friends, before that potential due to point charge, let us do one more important case. Again, whatever now you see is a derivation. Very popular 3 marks question for your board examination. In fact, you like your teacher if he uses this kind of language. Really don't see it as a derivation or 3 marks question, of course, because after that you forget everything, you don't remember anything. And that is why I never wish to speak in such language. 3 marks, derivation, important, right? Now, earlier discussion, I will make use and will find a relation between electric field intensity vector E bar and this another potential character of the field. Relation between field and potential, right? Earlier we have shown the same situation one more time. Supposing this is an electric field, don't forget these arrow marks because field lines always should show the direction. And this is point P and another point Q. P and Q are two positions inside the field, and Now again a test charge moved from P to Q irrespective of the path of force. So this is what is the path displacement of a test charge from P to Q against the Coulombic force, right? So let us assume an arbitrary electric field. When I am saying arbitrary electric field, the whatever result that we now arrive can be used for any electric field, that is field due to any of the configuration of the charges. Assume an arbitrary electric field of intensity, suppose E. Intensity E. That may be either uniform or non-uniform. It can be both cases because field is uniform or field may be non-uniform, and that is why intensity I am taking as E. If it is a uniform electric field, it is the same at each and every point. Otherwise, this E refers to electric field intensity at that particular point. So that when we are taking small elements, a large number of small elements, during that very small, infinitesimally small displacement, that E can be taken to be a constant. So that is how it goes. So need not mention, I have just stated that an electric field of intensity capital E, and now I say let a test charge Q naught, and of course always positive, is displaced again with all uniform velocity and all, displaced from P to Q, from P to Q, yes, against Coulombic repulsion, right? Hence work is done. Hence work is done, and that is given by dW is equal to, yes, dW is equal to, we write it as F dx for a small displacement, and therefore this dW is what is earlier we said E Q naught times, right? So E Q naught times, this is what is dx, and please do remember here it is as the cos theta term is there, since it is against the Coulombic force, that cos theta becomes 180, therefore I will here get negative sign, the negative sign for the case of against Coulombic force. Therefore here also, yes, don't forget that negative sign, which is very very important now. It's a great significance to understand. dW equal to minus of E Q naught times dx. If now I am saying this as dW by Q naught equal to minus of E times dx. And what is this dW by Q naught? This refers to dV. Remember, potential means potential at a point or potential difference. Even when we say potential difference, it is nothing but potential at a point also refers to potential difference with respect to your point outside the combination, outside the system where we have taken it to be zero potential, right? So dW by Q naught is equal to, therefore I will now write it as dV is equal to minus E times dx, and therefore this E is equal to negative of dV by dx. Yes, this is a very important expression. E equal to negative of dV by dx. Now you remember this is the same case of E referring to a force analog F, which is a conservative force, and that dV refers to an energy portion. Therefore E is equal to minus dV by dx is similar to F equal to minus dV by dx. Is it not? Electric field is the negative gradient of potential. The result is electric field is nothing but negative of gradient of potential. What is the meaning of that negative sign? Because here you say against Coulombic force and therefore we got that minus. So what is now the significance of that negative sign? Even this can be a 1 mark, 2 mark question for you in the board examination. What is the significance of that negative sign in this expression? Now I am writing for the significance of the negative sign. Right? So here I refer, right? With a star mark I am writing. With a star mark you can make it. Negative sign signifies, negative sign shows that, potential, which means electric potential always decreases. Hello friends, potential always decreases in the direction of electric field. I have no space here. In the direction of electric field. Is it okay? Negative sign shows that in the direction of electric field, potential decreases. What is the meaning of that? I show you now. What is the meaning of that significance? In a physical representation I am showing you. Suppose this is the case of uniform electric field, or else I will take another case of supposing this is how an electric field non-uniform I have shown in any of the forms. So this is how a non-uniform field is represented, right? Now when I refer to two positions, suppose here I take the position P and here I take the position Q. Two positions, look at that. P appears when you are moving in the direction of the field. P appears first, Q appears later. That is what is the meaning of in the direction of electric field. Here also I will show. Suppose if this is some point P and this point here referring to Q, right? Now according to this statement, you can make it out that V at P greater than V at Q. Why? In the direction of electric field, when you follow, the point P appears first and point Q appears later. So that is what is the meaning of that. Supposing here, if you take here also P and Q, look at these arrows, and that is why I have told you the arrow is everything when we are representing field by field lines. P and Q. Here also you will find that Vp greater than Vq. Like this. Like this. Remember, when we have given such case, also now you remember with respect to the electric field, this is a uniform electric field. Therefore, now here you will write it as Ep equal to Eq. Here in this case, field is the same, potential is different. Potential at 2 points are different, but field intensity is same. Is it not? Now, when you look at this case, now why I have given Ep equal to Eq, you tell me, because whenever we are comparing the intensities, we have to compare the density of field lines. That is what is flux we said. Flux density more, intensity more, flux density less, intensity lesser. Now here, since it is a uniform, flux density is same everywhere. Therefore, there is an Ep equal to Eq. Now look at this one. Now what is your observation you tell me? When you look at this point P, the flux is more dense. You will see clustering of these field lines. They are very closer to one another. Flux density is more. At Q, yes, the flux density is lesser. Therefore, you can have E at P greater than E at Q. Like that. So it's for, I have given this expression to understand the significance of that negative sign. Also, since we have given one relation that E is equal to minus of dV by dx, let me also show the same. Let me also show the same result, but with a small difference. What is that? Next board I will show you. So this expression, which is in the differential form, the same differential form, of course. Previous statement, if we take, I will show it as an integral form. Right? What is that? What is that? Yes, V means. Let me show. integral dv. Now integral dv here from point P to Q, that suppose you have taken point A to B like that. Suppose it is from P to Q. This is what is integral dv, which is equal to VQ minus VP. Any of the potentials can be 0 if it is taken a point at infinity. VQ minus VP equal to integral E bar dot dl bar, because since you remember this is nothing but a kind of dot product, the Fourier aspect refers to E bar dot dl bar. So VQ minus VP, this is what I simply call it. Suppose if I call this as V, what is V? V can be potential at a point and potential difference between 2 points. Symbol I am using. It can be either potential at a point. When I am saying potential at a point, right, the other point is at infinity. That is what is a kind of automatic, by default you will take it. So V is equal to integral of E bar dot dl bar. Of course, sorry, with negative sign. With negative sign, and that negative sign has a significance, especially when we are evaluating some numericals. That negative sign is a very important thing. So V is equal to minus of E bar dot dl bar. And the same expression also I will write as V is equal to the electric potential difference, right, is equal to E bar dot R bar, is also an useful expression that I consider. If E bar is a uniform electric field, suppose in the case of uniform electric field I will take V is equal to E bar dot. V is equal to E bar dot R bar. E bar dot R bar, this is what is E times R times cos theta. Of course, no other symbols in between. E R cos theta. So this V depends upon E, R and also this cos theta. Remember? I want to throw more and more light on this, but some people may feel it as a difficulty, and that is why I am now doing that. When you come back, we will do, if you are interested in our excess study, what sometimes evenings, we will do that. E R cos theta. Now what does it mean here? You see E R cos theta I can use for this uniform electric field. Now supposing if I take P and Q, both the points, this is what is R bar and this is what is E bar. R bar refers to that displacement, the position vector joining the initial point and final point. In this example, what you see is that I have shown R bar parallel to E bar, theta equal to 0, cos theta equal to 1. Therefore, you got V equal to ER. Supposing, of course, generally in most of the few examples, we'll be using V is equal to ER. But V is equal to ER can be used only when this P and Q, this R bar vector is parallel to E bar. Supposing in this example, electric field, this is again a case of uniform electric field only, electric field, whereas if this is what is point P and this is point Q, I have referred, and this is what is the displacement vector, the position vector joining P bar and Q bar, and this is what is E bar. Now you clearly see an angle between the theta. For such cases, I cannot use V is equal to ER straight away. So that's what is the meaning. V is equal to E times R times cos theta. Now for the case of cos theta is equal to 1, for the case of cos theta is equal to 0 degrees, that is E bar parallel to R bar, or R bar parallel to E bar, what you got is E is equal to V by R. E is equal to V by R. When we have told about the SI unit of intensity of electric field, it was the Newton per Coulomb. There I have told an alternate and pure electrostatic unit as volt per meter. Mention that at the right time we will come to know why this unit is volt per meter. Newton per Coulomb is equal to volt per meter. Why? Now you see here E, the electric field, referring here to V upon R. Remember please, V is equal to ER is not a generalized equation, it is for that specific case. And then E is equal to V by R, V for volt, R for meter, and that is what is volt per meter. Now, remember, when we have given the relation between potential and field, you can stop your board exam answer at this point. E is equal to negative of dV by dx, and explain the significance of that negative sign as well. That will finish your answer. After that, all these things are very essential if your slogan is a Dil Mange More, then certainly all these things are very, very important. Now look here, this is what is V referring to E bar dot R bar. Now this is also, when you observation is very keen, you identify many such things onto which you will give a focus, and you can make a good observation. Now this is field vector and a position vector, right? With respect to displacement. When such cases are there, now how to find the potential difference between 2 points? It can be a very tough example. If we are unaware of any of these fundamentals, simply writing a relation and forgetting is not sufficient. So here you see E bar dot R bar is nothing but V. V is the potential difference. It can be even potential at a point when the other point is at infinity, where the potential is 0. So this is what is present session. So we understood what is electric potential, which we have introduced as an analog of work or energy, and then we have defined electric potential and relation between field and potential. Therefore, in the next session we will continue this concept with more and more knowledge. Until then, eat well, sleep well, be positive, be in the mood of learning. We'll meet in our next class. Thank you.